Hello friends, in this video we learn a module 2 part C solutions of trusses. Let us see that in a module 2 part C we have two bits: stiffness of a truss element, derivation, numerical problems on trusses. So before going to drive the stiffness matrix of a truss element, we need to get the definition of truss element. What is mean by a truss? A truss is an element defined as a combination of a more than one bar or link element has a relative displacement in a space or global coordinate is said to be as truss element, which has a different structural application in engineering field. First bit is given in your syllabus, that is a elemental stiffness matrix for a truss element. We need to drive how to drive that elemental stiffness matrix for a truss element. We'll consider a truss element. All of you write down this truss element. If you are seeing my video, then separately I'll take this truss element and I'll explain in a plain sheet. See here, we have this element of a truss. Element of truss means one bar element separately we have taken from the truss. Truss means we have a more than one numbers of bar which has a relative displacement. It is called as a truss element. It is element number 1, element number 2, element number 3, element number 4. So four elements we have. For example, another truss, if I'll draw, this is another type of truss. What we have: element number 1, element number 2. Another type of example I'll give. This is another type of truss element. So we have this is element number 1, element number 2, element number 3, element number 4. Similarly, we have another type of a truss element. This is element number 1 and element number 2. Or we have another type of truss is this one. So element number 1, element number 2, element number 3. All the types of elements is containing a different elements, different shapes. So what is this element number 1? What is this element number 2? What is this element number 3? This element number 1 is said to be as a bar element number 1, bar element number 2, bar element number 3, or link element number 1, link element number 2, link element number 3. The combination of these elements has a relative displacement, with each other due to the application of a load. If I'll apply load here, the relative displacement with this node as well as with this node we have. For example, if I'll apply the load here, so the both nodes will be get displaced. So that means a combination of more than one bar element has a relative displacement with each other is said to be as a truss element. We got the idea what is meant by a truss. Now I'll represent that one of the link element separately, or one of the bar element separately. I have taken this as a bar element, has a two nodes. It is a part of the truss. One element will take y means we are driving the elemental stiffness matrix for a truss element. For example, I have drawn this as a truss. Assume this element I have taken is this one. First I'll drive the elemental stiffness matrix for this element, and then rest of the elements automatically will get, as usually we have drive the equation for bar element, right? So now we'll consider this element. So what I have considered a element is called as any truss element, has represented in a local coordinate system y dash and x dash, x dash and y dash. Any displacement occurs at this node, any displacement is occurs at this node, or any displacement occurs any direction that q is representing with the dash is said to be as a local coordinate displacement with respect to the local coordinate system. Similarly, if I'll represent that bar element in a Cartesian coordinate with a global system, you can see the global coordinate system is this one. The plane truss element in a global coordinate system is representing along x-axis, and y axis without dash. See here, you can easily realize without dash I have represented here, with dash I have represented here. So where we will see a with dash, will say a local coordinate system. Where we have without dash, will say a global coordinate system. So where we'll say a q dash, will say a local coordinate system displacement. Where we will see a q, just a q, will say that is a global coordinate system displacement in a space. Now we'll consider a separately this step by step process. See here, as I have shown in the last diagram, this is representing in a local coordinate system. That what is that, we need to find out a stiffness matrix of truss element as a one part of the truss element. This one is a one part of the truss element is taken, called as bar, has a stiffness matrix. We know that k is equals to k dash. I have taken y means the element is representing in a local coordinate system. We have this stiffness matrix. It is a part of the truss element. That is part of the truss element is said to be as a bar or link element. Bar means we have derived the equation that is equals to k is equals to a e divided by l, 1 minus 1 minus 1 1. I have taken as a k dash due to the element is present in a local coordinate system x dash and y dash. Same element as I have transferred in a global coordinate system, I have represented between the x and y axis. After that this element is displaced with respect to a local coordinate system from position 1 to position 2. The displacement of a truss element in a local coordinate from position 1 to 2. So it has been displaced from this point to the next point. This is the initial position and this one is final position of the element. After getting the displacement, we have the node number 1 has shifted from this point to this, that in a local coordinate system is represented as a q1 dash, and the node 2 parallelly shifted from this point to the next to this point is represented as a q2 dash. Then q1 dash is equals to question mark and q2 dash is equals to question mark, the displacement from first position to the second position. The displacement q dash in a local coordinate system, we need to find out at each node. Single degrees of freedom is considering in a local coordinate system. See here, q dash, q1 dash and q2 dash is a displacement at local coordinate system. Now convert that local coordinates displacement in a global coordinate displacements at each node. Consider the 2 degrees of freedom at each node in a global coordinate system. How it should be after converting that local coordinate displacement in terms of a global coordinate displacements. Let we see that in each node we are considering a 2 degrees of freedom. How it will be diagram itself, it will says that we have a displacement with respect to the x-axis. Node number 1 will get displaced along x-axis q1 and then along y-axis q2. So that means at node number 1 displacement will occurs along x-axis and also y-axis. Displacement along x-axis is represented as a q1 at node number 1. Displacement along y-axis is represented as a q2. Similarly, at node number 2 we have the displacement here at node number 2 along x-axis. Displacement will take place and then the y-axis displacement will take place, representing as a q3 and q4. See here, q1 and q2 be the nodal displacements at node number 1 has 2 degrees of freedom at each node along x direction and along y direction at node number 1. See here, similarly at node number 2 we have 2 degrees of freedom. What is the displacement along x direction q3 and displacement along y direction q4 be the nodal displacements at node number 2 has a 2 degrees of freedom in a global coordinates. In a global coordinates, I have not represented it as a dash. When we represent a dash, it is a local coordinate system. It without dash, it is a global coordinate system. After representing this one, we need to resolve this a relationship between a global and local coordinate displacement. Then we'll get a value of q1 dash and q2 dash. So to find that, we are doing this exercise in terms of a q1 and q2, q3 and q4. Now I'll draw a perpendicular line with respect to the axis of the bar element towards the q3 axis. This is a line, q3 for direction is parallel to this x-axis, and then I'll draw the perpendicular line from here. We can see this a 90-degree line with respect to the axis of the bar element from the initial position towards the displacement of this axis. See here, to this point we have drawn, and that is a 90-degree. It makes an angle of theta. Similarly, we have here axis 90-degree, so then this is a theta value, right? So now this portion is call it as any adjacent side for this triangular element, and then this one is a opposite side. Then similarly we have for this triangular element with respect to this axis and this inclination, I will take that separately. This triangular element we have like this, this is an axis, and we have this is 90-degree and theta. Similarly we have here this element like this, the 90-degree, and then this is a theta we have. So this one is an opposite side, and this one is adjacent side. We have this idea. Then we have this portion for this triangular element. This side is adjacent side, and this side is an opposite side. So now we can say that this line, when I'll draw, this is equals to adjacent side, means what is the displacement is occurring in a element hypotenuse q3. That means q3 cos theta. Similarly, this we have a hypotenuse q1. This is an adjacent, that value is equals to q1 cos theta. We know that cos theta is equals to adjacent divided by hypotenuse. Hypotenuse is a q1 at node number 1, at node number 2 is q3 is an hypotenuse. Adjacent is this one. Just we found this trigonometric function, we are very well known. Similarly, rest of the things we need to find out this question mark, that how we'll find. Now I'll consider this triangle. This triangle is parallel to this, this I have stated. I'll take the triangle here. I will take this triangle, this is 90-degree theta, this is the opposite side, this is adjacent side. We have this hypotenuse side, q4 hypotenuse side. So this side, opposite side, is equals to this value. So we'll find that this one, which is equals to sine theta, is equals to opposite by hypotenuse. So opposite by hypotenuse means this is equals to, hypotenuse is q4 sine theta. Similarly here we have a hypotenuse q2, opposite side is this one which is parallel to this, that is equals to q2 sine theta. So same equation I have shown in the derivation, just I have splitted that all the characteristics I have shown. Let's we see that completely. You can check out here. I have given q1 cos theta with respect to this q2 sin theta, q3 cos theta, q4 sin theta, right? So now what is this q1 dash is equals to this q1 dash which is equals to q1 cos theta plus q2 sin theta. Similarly, q2 dash is equals to q3 cos theta plus q4 sin theta. So after this two equations, how we got after getting the two equations, we have this equations, that equation where we are considering here cos theta is equals to L, sin theta is equals to M. Then this equation is yields to q1 dash q1 L plus q2 M, and then q2 dash q3 L plus q4 M. So cos theta becomes L and sin theta becomes M. Similarly, cos theta becomes L, sin theta becomes M. So then I'll say equation number 5. This equation we are converting in terms of a matrix. So how we are converting that in terms of a matrix? q1 dash and q2 dash vector will get and then I'll take q1 q2 here. From this common, I'll write this equation again in a understanding format. You can easily understand q1 dash is equals to q1 L plus q2 M plus 0 time of q3 plus 0 time of q4. Similarly, q2 dash is equals to q1 in 0 plus q2 0 plus q3 times of L, this one, plus q4 times of M. See, from this equation, if I'll take here q1 q2 q3 q4 common here, so here coefficient of q1 is equals to L, coefficient of q2 is equals to M, coefficient of q3 is equals to 0, coefficient of q4 is equals to 0. We have only q1 L, q2 M in the equation number 1. So that is the reason we have taken q3 and q4 is equals to 0. Then equation number 2 is generated with respect to the given condition of A are considered positions of the element that converted in terms of a matrix with respect to this q2 dash. We have q1 we don't have here. It will get start from q3. Means q1 and q2 is not there, 0 0 coefficient of these two values, and q3 has L. Here you can see L, and here you can see M for q4 coefficient. We have converted that equation in terms of a matrix. We have L M 0 0 and 0 0 LM. So when we'll multiply to this one, we'll get the same equations, two equations. Then we'll say this is called as an L matrix transformation matrix, L which is equals to LM 0 0 0 0 LM, and this is a global displacement vector Q, and this is a local displacement vector Q dash. Transformation matrix, this one L means. We have the direction cosines. In generally we can calculate the direction cosine L is equals to x2 minus x1 divided by LE. M is equals to y2 minus y1 divided by LE. Y means we are saying this one, the element which has here is representing in a global coordinate system. This element is representing in a local coordinate system, then it is transferred to the global coordinate system. So for that we have this one x1 comma y1 at node number 1. At node number 2 we have a x2 comma y2. So we'll take these two values to find out the value of L, that is equals to x2 minus x1 divided by LE, total length of the element. So this is direction cosine cos theta. So sine theta, which is equals to what we have here, y2 minus y1 divided by LE. Y2 means final node value along the y direction, and initial node value along y direction. Difference between these two values divided by LE is said to be as what? Sine theta. So we have that concept, sine theta and cos theta, that is equals to m. We have and then the element effective length of the element we can easily find with the help of distance equation. With the help of distance equation, what is the distance equation? LE is equals to under the root of x2 minus x1 whole square plus y2 minus y1 whole square. So this is a distance equation. To drive these values, these are the exercise we have did, right? So these are the very important values we are taking here. I have given x1, y1 are the coordinate values at node number 1, x2, y2 are the coordinate values at node number 2. Then LE is a effective length of the element by using the distance equation which we have derived in a plus 1 and studied utilizes to solve the problem in a plus 2 of your studies. How we'll find out the elemental stiffness matrix with the help of that previous concept, very important. The elemental stiffness matrix is equivalent to the one dimensional element when viewed in a local coordinate system. Hence the elemental stiffness matrix in a local coordinate system becomes k dash. In a global coordinate system without dash. In a local coordinate system with dash value, we have here dash, we can check out. We have here a dash. Without dash, we will say global coordinate system. With dash, we will say a local coordinate system. LE remains same. 1 minus 1 minus 1 1 will remain same. I'll say this is equation number 10. The elemental stiffness matrix for a bar element, KE. AE is the area of cross section, EE is Young's modulus, length, LE means effective length of the element. Let U be the elemental strain energy for a truss element. Local coordinate system is given by, we know that a strain energy of the bar element, that is U is equals to half into Q dash transposed K dash Q dash. Y means the bar element is representing the truss. What we are saying, the truss element representing along y dash and x dash axis. This is a local coordinate system. With respect to this, we have a displacement q dash, so that we know that strain energy, which is equals to half into k delta square. K means stiffness of the element, delta means displacement. Q dash transpose into Q dash means delta square. So we have this equation of a strain energy. That strain energy with respect to the local coordinate value is equals to half into Q dash transpose matrix into K stiffness matrix into Q dash. So that is equals to single prime value if we'll take representing as a local coordinate system. To find the elemental stiffness matrix in a global coordinate system, we know that we have derived this equation. This equation, remember it. You will ask me the question while I'll drive the stiffness matrix. That is the reason I have derived this equation. How it has been came, we have known, we have derived from the figure. We know that a local coordinate displacement is equals to a transpose matrix into a global coordinate system. How it has been came, we know that in the previous derivation, the substituting equation number 3 in equation number 2, that equation number 2 is a strain energy of the element. We need to substitute the value of this q dash. Two values will substitute here. So this value, then ue is equals to half into q dash is equals to lq transpose matrix into k dash. Q dash is equals to lq. I have substituted here, and then I'll rearrange that equation. I'll take common here q and q, and then properties of the material, I'll multiply with the square bracket. I will take L transpose matrix inside with the matrix K dash T, and displacement separately I'll take. This matrix is equals to a elemental stiffness matrix for a truss element. We need to find this value, just we need to rearrange. We know the value of this transformation matrix, that is equals to, we need to find first these two values. We know this K dash value. So what it means, we know this equation, we know this matrix, K dash is equals to A E divided by L E 1 minus 1 minus 1 1, this one. So then we need to get this L and L transposed. What is that L and L transpose? I have written T, it is not a T, that is equals to L. L and L transposed. L is equals to L M 0 0 0 0 L M. So we found this here, that is equals to L. So now L transpose matrix, row becomes column, column becomes rows. We have here L M 0 0 0 0 L M. So this is a transpose matrix of transformation matrix. So now that all the values we have here, see here, this is called as a global stiffness matrix for a truss element. K is equals to L transposed K dash L. So this we got from this equation, right? We have written here. So now after getting that L is a transformation matrix and given by, so L transpose matrix, we have derived this L M 0 0 0 0 L M. LT is equals to row becomes column, column becomes rows, right? So we have L M 0 0 0 0 L M 0 0 L M. So we have a transpose matrix converted, where we know that L is equals to cos theta, M is equals to sin theta, or the direction cosines. The stiffness matrix in a local coordinate system, we know that K dash is equals to AE divided by LE 1 minus 1 minus 1 1. Just now I have discussed. All these three values will substitute in this equation. Then we'll get a global stiffness matrix for a truss element. So now how we'll get that global stiffness matrix for a truss element? I will write here L transpose and K transpose L and K value first I'll take. I will take first here, first position L and K, these two values I'll take, simplify, and then I'll multiply this one. Okay, so now what I take here, L transpose matrix and K. So K means what? A E divided by L E 1 minus 1 minus 1 1. So we have here L 0 M 0 0 L 0 M. So we need to multiply first, this will comes, and then just I have rearranged here. So we need to take this row, this column for the multiplication. Y means this will come first, K L transpose matrix, and then K will come, then L will come. So based on the order only we need to multiply. So this in the row wise, first row with the first column, I'll take this is the row, first row, first column, L into 1 plus 0 into minus 1, and then first row, again first row, second column I'll take. So L into minus 1 plus 0 into 1. Similarly I'll take a second row with the first column, M into 1 plus 0 into minus 1, and second row, okay, second column is this one, M into minus 1 plus 0 into 1. Then I'll take third row, first column, 0 into 1 plus L into minus 1. Third row, second column, 0 into minus 1 plus L into 1. Similarly, I'll get next fourth row, first column, here 0 into 1 plus minus 1 into M. Again fourth row, second column, 0 into minus 1 plus m into 1. So then resolve this matrix, we'll get here. This will go 0, L into 1, L minus L becomes minus L, this becomes 0, m into 1 plus m, this becomes 0, minus m plus 0, 0 minus L, we have minus L, this becomes 0 into L, L we have 0 minus m, we have here 0 plus m. So here the matrix what we have, L minus L, m minus m, minus L plus L, minus m plus m. So this as it is remains the same, we have copied here. Then we need to go with the getting a global stiffness matrix. So we got the value of this two, we need to multiply the L matrix. K is equals to L transpose matrix K dash into L. So L means transformation matrix. So now we got this value, multiply the L value. L is nothing but a, here we have found LM0000 LM multiply to this matrix this value. Now resolve here with respect to row and column. This equation is order wise, in the previous one little bit has been changed, order wise all of you take down. So see here, first row first column we are multiplying 4 rows into 2 column into 2 rows into 4 column, we'll get a 4 cross 4 matrix. If we'll get a 4 cross 4 matrix, this now I'll simplify this matrix. Take down first row first column, we have first row first column is this one, first row first column L into L square already have taken, minus L into 0 plus minus L into 0. Similarly first row second column this one, L into m plus of minus L into 0. Similarly third row first column we have here plus L into 0 minus L into plus L. Similarly fourth column with the first row L into 0 minus L into m plus of minus L into m. So we got this first row is over. Now we'll go with the second row first column, this one we have m into L plus of minus m into 0, m into m plus of minus m into 0. Then second over, this is the second column. Then we have a third column m into 0 plus of minus m into L. So again fourth column we have this one m into 0 plus of minus m into m. Then we go with the third row first column, this value minus L into L plus of L into 0. Second column with the third row, here we have minus L into m plus of L into 0. Then L into 0 third column we have minus L into 0 plus L into L. Then again fourth column minus L into 0 plus L into m. Similarly we got here fourth row first column second column third column and fourth column. Then we'll simplify all these values will get here. So this L square, this will go 0, L square we have Lm we have here, this will be goes 0, this will be L into 0 is 0 minus L into L minus L square, this will be equals to 0 minus L into m. So we have this one. Similarly here we have Lm, this will be 0, this will be 0, we have m into m square, this will be 0 minus m into L minus Lm, and then we have next minus m into m, this will be 0 minus m square. Then we have next L minus L into L plus of L0, this is equals to 0 minus L square minus Lm into L into 0, this will be equals to 0 minus Lm. So then this will be equals to 0, L into L we have L square, and then here minus L into 0 we have L into m, we have this one. Similarly and next bit minus lm in plus lm m into 0, and this will be 0, lm minus lm, so m into minus m into m minus m whole square plus 0. So then this equals to 0, yeah, ml this become, I have taken lm, and then this value is equals to 0, m into m both are positive, plus m square. So we have this value as it is, this as it is we have taken here. Rest of the things we have found. Now I'll divide this two part for the remembering purpose. I'll make this four parts of the matrix for remembering very easily. How to remember this? We need to remember while we solve the problem directly. We need to take this matrix. This matrix is called as an elemental stiffness matrix for a truss element in a global coordinate system, right? So now how to remember this matrix I will show. So I will have make the four parts, L square Lm Lm m square, right? Similarly we have here L square Lm Lm m square as similar to this, right? So this one. Similarly here also we have L square Lm Lm m square, L square Lm Lm m square. Don't bother about sign convention. Later on we'll go with the sign convention. Now I'll take here this four part, this diagonal part is positive, first diagonal, and second diagonal part is negative. So first you remember it only if 1/4 of the part of the elemental stiffness matrix of a given truss element. The rest of the things sign convention, if you'll remember, you can easily write the matrix. How to remember this one? You remember this part only. So L square Lm Lm m square. By heard this one, L square Lm Lm m square. Then write down another 1/4 of the part here, L square Lm Lm m square, L square Lm Lm m square, L square Lm Lm m square. How will remember the sign convention? Will have, don't bother about the sign convention. I have make the four parts here, so you can go with that. First part you write down without sign convention like this, all the four categories. Then again come back to this point, first quadrant, second quadrant, third quadrant, and fourth quadrant. Write it down as per the condition. First quadrant value is negative, all four values minus L square, minus Lm, minus Lm, minus m square. Similarly it is a positive, all characteristics L square Lm Lm m square positive. Come to the third quadrant, all coordinate value what I have, this is not a coordinate, for a remembering purpose I am giving this idea. So how to remember this? So this is negative, minus L square, minus Lm, minus Lm, minus Lm square. So in a fourth quadrant, L square Lm Lm m square. So I'll give you the equation number 5, that is a global stiffness matrix for a truss element. Thank you for listening my lecture. In next class I'll take a problem on trusses.